very useful technique to analyze the nonlinear system, time varying system. That is a modern control technique. So let us consider physical system to be represented in a state-based model. So consider a mass spring damper system, a simple mass spring damper system. This is simple mass spring damper system. This main friction is negligible zero friction. Spring, dashpot, mass. F of t is the applied force. Displacement, velocity is the output. Okay. First we have to choose the minimum set of state variable. So based on the order of the system, this is second order system. So we can choose two state variable. Say, select displacement x of t taken as one state variable, x1 of t, then velocity taken as another state variable, x2 of t. So f of t is the applied force, this is an input, u of t, x of t is the output, displacement. So this is nothing but output y of t. Now write down the physical equation governing the basic law. So this is a mechanical system by applying Newton's second law under D'Albert's principle. Now draw the free body diagram of mass. Okay, mass is detached from the diagram. Represent all the applied force and opposing force. Draw the free body diagram of mass. The form is the applied force, input force. Opposing force offered by the mass, dashpot and spring. So these are all the opposing forces. Now applying D'Albert's principle. That is ultimate sum of force acting on body 0. So that means sum of applied force is equal to sum of opposing force. So what are the opposing force? Opposing force offered by the mass. That is mass. Force is equal to mass into acceleration. So acceleration in terms of velocity. So dt of t by dt. Similarly, opposing force offered by dashpot. D is the viscous friction coefficient. T into velocity. Where m is the mass. Okay. Then f of k, that is k, that's stiffness of spring, that is coefficient. K into x of t, that means the displacement, where k is the stiffness of spring coefficient. Now substitute. So f of t is equal to m d of t by dt plus d into d of t plus k into x of t. Okay, so this is equation number 1. Now replace this physical variable by the state variables. So f of t is u of t, m, d of t we taken as x2 state variable. So one time derivative, so x2 dot of t plus d into d of t we taken as x2 state variable x2. So x2 V of t replaced by x2. Then k x is taken as another state variable x1. So instead of x you put x1 of t. Now keep m into x2 of t, x2 dot of t, one side bring all other term into other side. So m into x2 dot of t equal to minus k into x1 minus b into x2 plus u of t. Again now divide by m whole equation. So x2 dot of t is equal to minus k by m minus b by m plus minus k by m x1 minus d by m x2 of t plus 1 by m u of t. So this is equation number 2. Then we have taken that is v of t is equal to x2. Now differentiate both sides with respect to time t. So dv of t by dt is equal to x2 dot okay. Then similarly velocity v of t is equal to one time derivative of displacement. So dx of t by dt nothing but x taken as x1. So x1 dot okay. So v of t is x2 we taken as another state variable. So x1 dot is equal to the x2. So this is equation number 3. Now write the equation 2 and 3 in matrix form. Equations 2 and 3 in matrix form. What do you get? x1 dot of t, x2 dot of t from equation 2 minus k by m x1 coefficient x2 coefficient minus b by m. For equation 3 only we have x2 coefficient, x2 variable is there is no x1, so put x1 coefficient 0, missing coefficients. So x2, so that coefficient is 1. So x1 of t, x2 of t, plus from equation 1 u variable coefficient 1 by m. For equation 2 there is no u term, input term, so put 0. So this is state equation. This state equation, then so y of t output taken as x of t is nothing but x1 of t. So y of t is equal to the x1 coefficient is 1, there is no x2 term, so put 0 the x2 term coefficients. So x1 of t, x2 of t. So this is an output equation. So state equation and output equation is a state-based model of the given physical system. State equation and output equation is a state-based model of the given physical system.